Hi there and welcome from Ventura, California to today's webinar, the second of a three-part series making up Unmanned Systems Week. Today's session, titled GNSS Inertial Plus Integration for Unmanned Systems, is sponsored by Sensinor and Inside GNSS and hosted by WebAttract, the leaders in thought leadership webinars. My name is Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they explore the positioning technologies that can be integrated with GNSS and their implementation on platforms for use in the various operation domains. You'll also have an opportunity to have your questions answered at midpoint and at the end of today's presentation during the Ask the Experts panel with all three of our panel members. Now, we've invited a diverse audience registered from 42 countries and 28 states and provinces, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, Director of Business Development at Inside GNSS, would like to take a moment to welcome you and to introduce Mark Petavello, who will be moderating the main portion of today's webinar. Over to you, Richard.
Thank you, Lori. On behalf of Inside GNSS Magazine, our sponsor Sensinor, and our panel of experts, I welcome you to this second installment in a three-part web seminar series on unmanned systems. Today's subject is GNSS Inertial Plus Integration for Unmanned Systems, sponsored by Sensinor. We'll explore the positioning technologies that can be integrated with GNSS and their implementation on platforms for use in various operational domains. We'll also take a closer look at how sensor performance impacts overall system performance. Now it's time to introduce our moderator for today, Dr. Mark Petavello. Mark Petavello is a professor in the Department of Geomatics Engineering at the University of Calgary in Alberta, Canada. He works in the area of positioning and navigation and is a member of the Position, Location, and Navigation Research Group, where he conducts research using GNSS, software receivers, inertial navigation systems, and other multi-sensor systems. Mark received both his Bachelor of Science and PhD in Geomatics Engineering from the University of Calgary. Welcome, Mark. We're delighted you're here.
Great. Thanks a lot, Richard. And I'd like to extend a warm welcome to everybody out in the audience today. You're fortunate to be able to participate in what I think is a really excellent panel of experts, having to hear what they have to say about multi-sensor integration. And hopefully at the end of this, you'll be able to take away some useful information that you can apply to your product or project or application. So before we get going, we'll start off with our first poll question, and I'll turn it over to Lori to take care of that.
All right. Thank you so much, Mark. And folks, coming up on your screen, our first poll question: what kind of environment are you most interested in operating your unmanned system in? Is it open sky, indoor, underwater, urban, or under foliage? All right, we have 72% saying open sky, 21% indoor, 10% underwater, 47% urban, and 17% under foliage. And Mark, just wondering how this stacks up against what you were expecting.
Well, I think these results are quite interesting. I think it demonstrates that there's obviously a wide range of applications out there, and I think throughout the course of the webinar today, we're going to be able to see how the different technologies can tackle these different areas. So I think it should be good. So having said that, it's time to perhaps give a bit of an overview of what happened on Monday. As was said, this is the second installment of a three-part series. So on Monday, the focus was really on GNSS-only systems, looking at an overview of unmanned systems and their applications and some of the appropriate metrics used to evaluate these different systems. Then looking at the positioning requirements, again, from a GNSS-only perspective, the key challenges, the role of multiple GNSS systems, and of course, the issue of reliability, including interference and jamming. And then also the GNSS accuracy requirements, which is obviously very dependent on your particular application needs. So they looked a little bit at standalone and differential processing, as well as PPP, and also GNSS attitude systems, which can play a very important role in these particular systems. And then finally, there was some discussion about how these systems apply to aerial and marine systems. Now today, the main focus is on the integration of GNSS with other sensors, primarily inertial and whatever else is available or perhaps necessary. So we'll start off with an introduction of GNSS inertial and these other sensors and systems, and the role and benefit of these other systems compared to GNSS and GNSS inertial. We'll then move on to some of the integration strategies, what the limitations of GNSS INS alone are and how to include other sensors, specifically what types of integration strategies are available. And then we'll wrap things up with a nice discussion about product development. So once you've identified your sensors, or perhaps how do you identify your sensors, how do you put all these things together into some type of a practical system? So I think all in all, this is a very well-rounded presentation, and I think you guys will enjoy it. So having said all that, we will start off by introducing our first panelist, Dr. Martin Ochtahag, who is the Edmund K. Cheng Professor of Electrical Engineering and Computer Science at Ohio University and a principal investigator with the Ohio University Avionics Engineering Center. Martin obtained a master's degree from Delft University of Technology in the Netherlands in 1994 and a PhD in electrical engineering from Ohio University in Athens, Ohio in 1999. He has over 2 decades of experience in GNSS and inertial. His current research focus is very relevant to today's discussion and includes sensor integration methods using laser, vision, GNSS, and inertial for both manned and unmanned vehicles, terrain reference navigation, synthetic vision systems, aerial vehicle surveillance, and collision avoidance systems, as well as other aspects of aeronautics. He's a member of the ION, senior member of the IEEE, and an associate fellow of the AIAA. And he was awarded the Institute of Navigation's Thurlow Award for his contributions for laser-based navigation. And Martin's going to start us off today setting the stage, talking about GNSS, inertial, and other sensors, and a general overview of the integration strategy. So Martin, I turn it over to you.
Well, thanks, Mark, for the nice introduction. So if you look at my first slide, I will be talking first about summarize some of the applications of GNSS within the unmanned vehicle kind of community. Then I'm going to expand that a little bit to include additional sensors that are already available on some of these unmanned vehicles. And after that, I will start to look and address the operational requirements that are imposed by the function that these unmanned vehicles have and need to perform. Then finally, out of that comes kind of a need for integration with other sensors. So the first step I'm going to do is why we would want to integrate with inertial. And then, of course, for some environments, you need to even go beyond integration with inertial and integrate with additional sensors. So basically, if you look at GNSS, you really, on a platform, that the role of GNSS on a platform is there's a large variety in that role. The basic thing, the first thing that comes to mind is navigation of these platforms, determining its position and velocity in 3 dimensions. But besides that, for a lot of cases, you also need to come up with a surveillance function where a particular platform needs to know where other platforms are. For example, for logistics purposes. Then logically from that follows the conflict detection and resolution function, where you want to avoid getting into collisions with other vehicles around you, and where you require position information to be exchanged to find out if potential conflicts will arise. Now then, the fourth bullet that I have over here is the georeferencing capability. For a lot of these applications nowadays, they involve some kind of mapping of the environment. In these cases, these maps are often needs to be expressed in a geographic reference frame, and GNSS is really one of the big enablers there. Finally, there is also a large variety of new applications coming up in which timing, timekeeping, and synchronization is very important, and GNSS plays an extremely important role in that particular development. So if you look at these GNSS systems nowadays, and you look at, for example, the low-cost GNSS application in unmanned aerial vehicles, unmanned ground vehicles, you see that it really has enabled a lot of automation in these particular platforms. What you see here is the 8-level Sheridan scale of automation, and you see that already currently you can buy platforms that are relatively low cost for example mapping applications, where GNSS enables you to determine a flight plan on a user interface, and then the platform itself automatically executes optimizes and executes this particular flight plan. what you see here, that it's very important that GNSS will be reliable, that it will be available and continuously available throughout this whole flight plan. It could potentially lead to problems if GNSS would drop out, for example. Yeah. So if you look at the other sensors on board of these platforms, you see that GNSS is not alone. A lot of times, and you see this is actually in most vehicles, there is some form of an inertial sensor on board that is being used for the basic control of the vehicle already. Yeah. So GNSS combined with inertial is really kind of a logical choice. And we'll talk about later why that is really. In addition to inertial, there's also a variety of other sensors on there that just have to do with the actual intended function of this platform. If it's a mapping platform, they may have already cameras or laser scanners on there for the mapping function. So for example, the platform that you see on the left is really to perform mapping, but also to perform mapping for search and rescue operations. And there are cameras on there to perform that function, but could potentially also be used for a navigation-related function. On the other side, you see the Google car, and even though navigation is mostly performed by GPS and inertial and wheel encoders, for example, there is some other sensors on board, like laser scanners and radar, basically to come up with maps to identify traffic items, to estimate the speeds of these traffic items, and a variety of other functions. So you see, additional sensors are available. Now, if you now start looking at the operational environments, you see that the operational environments completely depend on your intended function. It depends on where you need to operate this vehicle for the thing that you want to do with the vehicle. So I kind of split it out in national airspace, open sky, under foliage, suburban, urban, and indoors. And what you see if you look at the right side column is that not for all of these environments is GPS available or GNSS available. In some of these cases, GNSS may be what I call challenged. That means you may not necessarily have the 4 satellites available that you need to calculate your position. Yeah. Or in some cases, like indoor, there may not be any GNSS signal available, or the signal strength is so low that you need to start come up with very advanced receivers to actually be able to track the GPS signals. What is nice, though, is that these internal environments allow you to use additional sensors. Now, there was already a previous Inside GNSS seminar that actually, or webinar that talked about the use of UAS in the national airspace. And so I don't want to talk about it too much, but what's important to realize is that if you use GNSS, for example, for navigation on these platforms, then now, and you need to certify this platform for operation in one of these airspaces, you have to also realize that your receiver that you have on board may need to adhere to standards that are kind of set by the Federal Aviation Administration or whatever agency will be take care of that. So what you see is that also means that your receiver will become more of a safety critical component, have to adhere to all these rules regarding to hardware and software, and may become as a result a significantly larger portion of your platform. So on the other hand, though, what I see for a lot of the applications is I envision a lot of stuff going on at lower altitude, and not just in rural environments, but also in populated areas. A lot of applications like mapping and search and rescue, law enforcement need to take place at lower altitudes in areas that may be populated. So some of these rules that, okay, you need to stay away from the population may not necessarily be as applicable for those, because you need to operate in these environments. And what is tricky about these environments is that GNSS is really challenged in these particular environments, like I said. So let's go look at it. So if I now say, let's focus on navigation, I know that navigation really means to determine your position, velocity, and attitude in time, to actually establish a trajectory in space. Well, this comes associated with a required navigation performance, where you not only are interested in the accuracy that your intended function must have, but also the integrity, availability, and continuity. And what do I mean by integrity is that if I have a particular position solution with a particular accuracy, and I'm not be able to meet a particular level of performance, at least tells me that I'm not meeting that level of performance. Availability and continuity are maybe a little easier to understand. It just means that I have a navigation capability when I start with my intended function. In other words, I have GNSS available to calculate my position. And continuity means I have a continuous operation of the navigation solution without any interruptions. Now, what happens is for a lot of these more challenging environments that I talk about, GNSS may not necessarily be available. There may be a continuity issue. So integrated navigation, what you're really trying to do is try to combine GNSS with multiple sensors to actually meet the required navigation performance as set by the intended operation that you want to support with your platform. Now, this is purely for navigation, but similar concepts do apply for the surveillance, collision avoidance, path planning functionality that you may have on board of your platform. And the logical first choice is to say, well, let's integrate GPS or GNSS with inertial sensors. And what I did on the next slide, I just give you kind of an impression of some data that we collected in Columbus area. And in this case, you see that due to the fact that there's buildings, structures, shadow regions, you see GPS gets not necessarily the continuity that you need. So in this case, an integration with inertial will allow you to at least fill in all the gaps that you're seeing on this particular slide. However, there still are areas that are not optimal. They're still pretty much challenged even with an inertial. And for that, you may want to actually go beyond GNSS inertial to GNSS inertial plus some other sensor. Yeah. So, and here's kind of a set of pictures in one of the scenarios that we are looking at, where we're outdoor, we're flying around with a kind of a mapping UAV. We're getting close to a building. We're transitioning from an outdoor environment to an indoor environment, and in the indoor environment, really we lose GNSS and we have to kind of start coasting on inertial. So in that particular case, depending on inertial, your position will drift away, and you may need to say, well, okay, we may have to look at other integration methods to work this. So one thing that you can do is actually exploit the environment. So you can start saying, well, I'm going to look at the environment with a set of sensors that are available. And the ones that I really focus on in this particular presentation are really mostly the active ranging sensor, the LiDAR, the laser scanner, and the visual sensors like cameras. But there's a variety of other sensors available there, like beacons, etc., and odometers. Now, the taxonomy that you see in this particular slide is basically dependent on sensor technology. Later on, both Andre and Sandy will talk about looking at it not from a technology perspective, but looking at it from a measurement perspective, or whatever the output is from the sensor instead of the technology. Now, so basically the approach will be to actually take the inertial, which is a sensor that's more or less always available, has a very good continuity, and then integrate that with, of course, first of all, the GNSS receiver when you have GNSS available, but then also add, for example, vision sensors and laser scanners. And in these particular cases, the core sensor will help performing motion compensation, for example, for these vision and laser scanner sensors. But on the other hand, you can also take these sensors that you already need to use for the original function, the original intended function of the platform, and use that to augment your navigation solution, to augment your inertial solution, to estimate and reduce your drift errors that are present in these inertials. And Andre will talk in a lot more detail about what the techniques are to do so. So in my particular case, I have two examples. First of all is one of the platforms that we have. This actually has a large variety of sensors on it, and the basic premise is that this platform's intended function is to take off outside, fly indoors, perform a mapping function, perform the identification and location determination of certain features in the environment, and then take that information and map it. So in this particular case, you see we have a GNSS, we have an inertial there, but we also are having a variety of other sensors, like a couple of laser scanners and cameras, to kind of map the environment. So what we did, we also took these sensors and actually used them to establish a more robust navigation solution in the indoor environment when we have no longer any GNSS available. Now, there's a lot of issues associated with interfacing these sensors to one another, and Sandy will have like a lot more detail on what are some of the guidelines that you need to worry about when you start integrating these sensors. And timing and synchronization is really a major concern there. Another example would be in kind of a basic mapping application where we're outside in the open sky, but you still will need GPS and inertial just to get a robust solution, but also to get a pointing, it's like an attitude determination for your pointing angle of your sensors. So in this particular case, you see we actually were able to fly an autonomous trajectory based on GNSS position. We took camera imagery that was georeferenced and time tagged, and it was used to kind of perform a 3D reconstruction of the environment that then is somehow also tied to a GPS solution. So that is that. So I want to go back to you, Mark.
Great. Thanks a lot, Martin. I think that's a really good start to the webinar and really sets up the problem very nicely. And so we'll now lead into the presentation from Andrei Soloviev, who is the president of QNAV, an R&D business enterprise. He has previously served as a research faculty member at the University of Florida and as a senior research engineer at the Ohio University Avionics Engineering Center. He's very well known in the industry. He has authored and co-authored more than 80 navigation-related publications, and his research interests lie mainly in the area of sensor fusion and signal processing for navigation. And Andrei is going to take us into more of the details regarding the integration. So Andrei, I leave it up to you.
Well, thank you, Mark. It's a pleasure to be here today. So I'm going to talk a little bit more details about different integration techniques, how you combine GNSS with inertial, and also how you extend beyond GNSS inertial integration and include other sensors into your multi-sensor fusion navigation solution for autonomous systems. So the topic of GNSS inertial integration has been covered in a fair amount of details in previous Inside GNSS webinars, so I'm not really going to spend too much time here, but rather just summarize the main principles of integrating GNSS with the inertial, specifically as it applies to unmanned vehicles. So as you probably know, there are three main integration strategies: loose, tight, and deep integration, where you integrate inertial and GNSS data at the solution level for the loose integration, when you go a little bit deeper and you integrate at the measurement level for the tight integration, and finally the ultimate, so to speak, integration solution is the deep integration, where you perform data fusion at the level of signal processing. So main benefits is obviously is improved availability of the PNT. You can bridge over GNSS outages for GPS or GNSS challenged and GNSS degraded scenarios. There is an ability to check the measurement quality, specifically when, for example, you are in an urban canyon and some of the measurements are severely corrupted by the multipath. Combination of GNSS and inertial gives you an option to check and detect those bad measurements and not use them for the navigation solution in order to avoid severe degradation in performance. And finally, there's an improved robustness of the signal processing. For example, deep integration, you can extend the integration interval within the GNSS receiver and enable tracking of extremely weak signals and suppression of jamming. And also you can do things like a spoofing detection when you integrate in GNSS with inertial. And just to exemplify the benefits of the GNSS inertial integration, here is a couple of examples on this slide for the application navigation under the foliage. And the GPS-only solution, you see there are very sparse fixes that are obtained based on the GPS only. Essentially, when we are out in the open, GPS solution works, but under dense foliage coverage, there's just not enough signal strength for the GPS receiver to track and recover those signals and derive the navigation solution from there. So pretty limited capabilities based on GPS alone. When we switch to deep integration of GPS and inertial, then the situation improves dramatically. What you see is the reliable reconstruction of the trajectory for the entire test scenario. So it just illustrates benefits of integrating GNSS inertial and specifically doing that at the signal processing level for this example. Going to the next slide, as Martin was saying, GNSS inertial integration is really useful to improve and overcome some drawbacks of the GNSS only navigation, but it has some limitations as well. Specifically, when we're talking about autonomous vehicles, sometimes, maybe most of the time, you sort of limited what kind of budget you have for the inertial and what type of size, power, and weight constraints you have for the inertial measurement units. And as a result, you can't really use, in some cases, or maybe most of the cases, very sophisticated inertial sensors. You have to deal with lower quality, lower grade sensors. And as a result, just the drift of the inertial navigation solution will increase. So this is an example here, navigation in dense urban area, downtown Detroit, essentially when you're out in the open or even go in a sort of not a very extreme urban canyon scenario, the solution still works pretty reliably based on the GNSS inertial. However, if you're really in the extreme situation of a deep urban canyon where you may have, one or two satellites or maybe no satellites at all, then there is a significant discontinuity. Inertial starts drifting, and you cannot rely on the GNSS inertial integration anymore. So that's the motivation to go beyond GNSS inertial integration and add other sensors to it. And as Martin was saying, there are other sensors available on autonomous platforms, such as vision sensors. There may be pressure sensors, magnetometers that are not necessarily there for navigation purposes, but we can use them to improve our navigation capabilities as well. So what's the integration approach? Obviously, we want to keep all the main benefits and all the techniques that we've developed and tested before for GNSS inertial as much as we can, and extend those techniques for cases where we add additional sensors to the system. So we don't have to redevelop everything from scratch, and we can rely on previous benefits of GNSS inertial integration. So the approach is you want to use inertial as a core sensor. And the reason is obviously it's a completely self-contained solution based on inertial. It doesn't depend on the environment. You cannot spoof it. You cannot jam it. It doesn't depend on any type of external signal. So it's self-contained, but it drifts over time. So other sensors are used as aiding sources to reduce drift in inertial navigation outputs. So the generic integration approach, basically you have some measurement from a secondary sensor that provides aid measurements for the inertial. And in general case, this measurement is some nonlinear function of your motion states, position, velocity, attitude, and sometimes you want to include sensor biases in this formulation as well. And then there's a measurement noise. Can probably assume it's white or something like that. So you have this actual measurement function, and then you compute the predicted measurement based on the inertial. The same function, same nonlinear function, but function of the inertial position, velocity, and attitude states now. Then you take the difference between your INS predicted measurement and the actual measurement, and that difference provides you an observable to estimate drift in inertial navigation outputs. And in terms of the estimator, the most popular estimator still is the extended Kalman filter, because most of those measurements you can pretty efficiently linearize and essentially get away with the linear Kalman filter estimation techniques, which is very efficient and can be implemented in a lot of real-time systems in a very straightforward way. However, in some cases, you want to go beyond extended Kalman filter and look into nonlinear estimation techniques as well, such as uncentered Kalman filter, sigma points, or particle filters or marginalized particle filters. One of the important points here is that really it doesn't matter if it's an extended Kalman filter or nonlinear estimation technique. We still want to formulate the filtering in terms of the complementary filtering approach. So we're not estimating the motion states themselves, but rather we're estimating errors in the inertial computation of those motion states. As a result, the linearization becomes easier, and modeling of the system dynamics becomes easier as well when you model errors instead of modeling the actual motion. So the next topic is, that was the main principle of integrating GNSS inertial and adding other sensors to the system architecture. Let's talk how we can actually use some of those other sensors for extension of the GNSS inertial integration. And one of the very popular options for adding for another sensor, another navigation technique, is what I would call image-based navigation. The motivation for it Well, it's basically a perfect augmentation of the GNSS-based navigation. In GNSS denied scenarios, what you generally have is some kind of an obstacle. It's man-made or natural obstacle that blocks your GNSS signal or essentially attenuates it to the level where you cannot recover it anymore. So that's a problem for GNSS navigation. However, this obstacle can generally provide you a fairly good landmark for the image-based navigation approach. So you see these two approaches, GNSS-based and image-based navigation, are quite complementary to each other. If there's a wall of a building and you cannot track your GNSS signal because of that, then that wall gives you a landmark for the vision-based or image-based navigation. If it's an open, no landmarks, GNSS-based navigation is good enough. So the main principle of the image-based navigation approach, you first record an image of the environment, such as a video image or an image of the environment with the laser scanner, two-dimensional laser scanner in this example. Then you extract navigation-related features from that image, such as point features from the traditional images, video images, or lines, actually fairly reliable features for the laser-based navigation. And then you use those features as navigation-related landmarks. Essentially, use changes in feature parameters for navigation. Here's an example of improved availability when you combine GNSS, GPS measurements in this case, with the laser scanner for navigation in an urban canyon. So the situation here, essentially, you see two satellites from GPS, and if your clock is calibrated, and in this case, you can determine along the track a position component from the GPS information. However, it does not give you any information in the cross-track direction. And this is where the laser comes in. For the laser part, you basically have these two walls that you see in your image of the laser scanner. And you can tell how much you moved in between these two walls. In other words, you can determine a cross-track component of the position. But the long-track component of the position is not available if you're looking at the laser-based solution alone. When you combine GPS and laser, in this particular case, then your position becomes completely observable, and you can derive a complete position fix from this combined GNSS and image-aided navigation solution. There are two main techniques to navigate based on images, and the first one is the feature-based navigation approach, what I talked a little bit already, and the second one is what's called the correlation or map-based approach. Essentially, for the feature-based, you extract in features and you operate in these specific features. For the correlation-based approach, you're looking at the entire image and you derive the information, how much you moved or how much you rotated, by correlating images between two successive measurement updates. And inertial is still very useful to improve the robustness of the overall solution. For example, inertial can be applied to robustify the feature matching process. It can also be applied to improve or reduce the search space for the correlation-based techniques. So inertial is still very important to have it there. So a very simplified, straightforward conceptual explanation how you actually navigate based on features. In this case, there's basically a case where you have a wall in front of you and you observe this wall in the image of your laser scanner as a straight line. And you make a displacement. So in the first image here, you're at this point and you measure this distance to this line in your scanned image. Now you moved, you're in the second point here, and again you measure the distance to the line in your second image. And essentially it's very straightforward. In this case, the displacement is exactly the difference between these two ranges in scanned image 1 and scanned image 2. So obviously when we go into complete 6 degree of motion situation, it gets a little bit more complicated, but the main principle is still the same. You're looking at the changes in feature parameters between two images, two laser scans in this example, and you derive navigation-related information from there. These are the benefits, example of the benefits of combining GNSS with inertial and adding other sensors to it. Example of the GNSS inertial LiDAR data fusion in an urban canyon. In the previous example, when we just had GPS and inertial, there was some discontinuities in the solution. Now it's a continuous trajectory reconstruction for the entire very dense urban scenario. So as Martin was saying, there are really a bunch of other sensors on the platforms. And in some cases, we are really interested to add those sensors into the solution. But the current approach for the multi-sensor mechanization, the sort of the limitation of this approach is that it's very sensor specific. You develop your solution for GNSS inertial and laser integration, for example, but then you want to add a video camera or hallway layout for the indoor scenario as this information becomes available. And generally, you have to redesign your system from scratch. So the ultimate solution to me would be to design a sort of a plug-and-play sensor fusion that can accommodate different sensors by reconfiguring the software solution. And there are two different aspects of it. There's a hardware aspect. You need to make sure that you can talk to your sensors adequately and you can perform the time synchronization between these two sensors in an appropriate way. And Sandy will talk about this aspect a little bit later in this webinar today. But also just the software reconfiguration, how do you actually build a generic plug-and-play sensor fusion solution is a very interesting aspect. So I'm going to talk a little bit more about it. So it's very difficult, if not impossible, to create an exhaustive list of all possible agent sensors and reconfigure the solution in this way. However, it is possible to categorize all various types of sensors you can think of based on the type of the measurements that they provide, and then abstract the filter design based on those generic sensor classes. And then it's an object-oriented filter design that can be truly reconfigured before your operation when you plug and unplug different sensors, or even on the flight when different sensors become available. Here's an example of such generic measurement observable, which is a relative position observable, formulated not exactly as a relative position, but as a change in position vector projected onto some axis or axis of navigation or body frame. And this generic measurement observable can cover a fairly large variety of different sensors, odometer, position change from a 2D LiDAR, and even a three-dimensional LiDAR. Planar surfaces extracted from consecutive LiDAR images can be covered by this generic observable. Let me show you some example test results of this generic plug-and-play solution, the urban navigation, where we have really a bunch of different sensors working in a plug-and-play manner. Basically, it's the same software used for different scenarios, and in this specific case, it's reconfigured to address the sensor configuration that's summarized on this slide. And as a result, we can ensure reliable navigation in an urban scenario like the one shown here. And an indoor case, again, the same software, but reconfigured for the specific set of sensors. In this case, it's an indoor navigation, and outdoors, we're still relying on the GPS for the initial part. And then once we get indoors, we're basically navigating based on the inertial, camera, a barometer, magnetometer, and some RFID tags placed along the trajectory. So this just illustrates the capabilities of the plug-and-play sensor fusion solution, which to me is probably the ultimate solution for autonomous vehicles and navigation of those vehicles in different environments. So that completes my part of the talk, and I'll give it back to you, Mark.
Great, thanks a lot, Anya. You provided a really nice overview of some of the challenges associated with integration, but as well some optimism for how these things might actually be able to deliver a very useful product and solution at the end of the day. So we're at the time to start our first Q&A session to ask the experts. So if you haven't already done so, please feel free to go ahead and type in your questions into the system, and we'll try to get those addressed as best we can. We'll start off with a question to the entire panel, and I'll start off with Martin. This one's from Anis, and Anis asks, what is the main difference between the challenges facing position solutions for manned versus unmanned vehicles?
I think if you look at this from a navigation perspective, where you need the position solution, kind of to navigate these particular vehicles, I think one important challenge is to realize that the position solution in a manned vehicle, let's say a failure of the position solution algorithms for a manned vehicle may not necessarily have the same consequences, because there may always be an operator or like a person there that can then use, as long as you can identify that there is a failure, then can still take action and try to mitigate the situation. For an unmanned vehicle, that may not necessarily be the case, or that person may be located at a location far away. So then you have to deal with additional issues like communication. So this has also consequences for the kind of the availability, continuity, and integrity of the solution, as well as maybe the capability to predict ahead in the future. So I think the fact that you have to look at the system as a whole and the fact that the navigation is just part of it, you really need to consider the human that actually has to use that navigation solution.
Great. Sandy, anything to add to that?
Yeah, just really kind of seconding a lot that Martin said there. When you're unmanned, you don't have that human to fall back on, the human that can interpret things like, say, a sharp discontinuity in your position that's resulted in a change of constellation or a sudden multipath kind of instance. So when you're feeding an unmanned system, it's all about the numbers, and there's no contextual sort of interpretation, or there's much less of it anyway. And especially considering that unmanned vehicles are often doing the, dull, dirty, and dangerous jobs. When they're dangerous jobs, your requirements for not only a very high quality position, but a correct quality indicator with it are really even higher. You might not be dealing with loss of human life anymore, but it could be loss of very expensive equipment.
Great. And Andre, anything else?
I agree with Martin and Sandy. The reliability and robustness for the unmanned systems seems to be way more critical as compared to manned application. But I also want to point out that it really depends on your application in terms of the requirements and how challenging it is when you go from unmanned to manned vehicles. For example, if you're interested in indoor surveying at the centimeter level for construction applications, that's obviously a bit more challenging than if you just want to fly your UAV in open areas through some waypoints at a meter level accuracy, or accuracy of a few meter level.
Yeah. Great. I think this really speaks to the challenges facing these systems when you go unmanned. The next question I'll direct to Sandy, and if others want to chime in afterwards, you're welcome to. This is a question from Edward, and he was interested in specifically unmanned aerial systems, but I think the question really applies to greater applications. Talking about typical GNSS, INSS systems, do they provide any redundancy in positioning? And then as a follow-up, how high-end of a system do you need in order to ensure a fail-safe landing, or just in general to a successful mission for whatever your application is? Okay.
Well, unfortunately, a lot of this answer is it depends, but I can kind of discuss the parts that are around it there. So does a GPS INS system provide redundancy in positioning? Well, absolutely, if there's some interruption in your GPS signals. So you've encountered a blockage, or I don't know, you have an antenna connection failure, something like that. You're not able to get a full view of the sky, or you've either lost all your signals or you've reduced the amount of signals that you're able to track. So in that case, yeah, the INS will absolutely bridge through position and velocity and continue providing attitude for you as well. And then, of course, the errors present in that position, velocity, and attitude will start to drift the longer it goes unaided. So the question is really, what else do you have for aiding? If you have just lost GPS because of a partial obstruction and you're still carrying on with, maybe 2 or 3 measurements, you can probably hang on to a decent level of accuracy for quite some time. So decent level of accuracy. Now that really depends on what the requirements of that landing is, what the craft is, if there's anything else you're relying on, like some sort of, a height approach type of information. So for how high-end of a system, kind of some rule of thumb numbers based on my experience with a SPAN product. If you're using a high-end tactical grade IMU like an LN200 or an HD1700, if you had a total outage for a minute, so you had no other aiding sources, you're on free inertial for a minute, you'd be looking at around 2 meters of position error out of that 1 sigma. So that's fairly high, depending on what you're landing. But if you were able to hang on to, maybe 3 satellites through that, your total positioning error at the end of the minute could easily be down underneath a meter, maybe even down to half a meter in there. Whereas if you went to something that was a purely commercial MEM, you could be dealing with tens of meters of error at the end of that 1 minute outage. I hope that gave a little bit of a guideline on that,
okay,
or what kind of errors to expect.
Yeah, it's a tough question. Martin, Andre, anything to add to that?
No, I think it was,
I think
pretty complete.
Okay, very good. I think we'll ask one last one before we head back to the presentations. So I'll turn this one to Andre. This question is regarding your plug-and-play integration that you mentioned. How do you handle the different error characteristics of your sensors, either in terms of noise or in bias or in-run bias and these types of things?
Well, it's a great question, Mark. Basically, it's all in the model. You have your measurement model, which is, again, a function of your nav states plus biases plus sensor noise. So you just need to adequately describe the measurement model and the error of that model in your filter. And then if you do that, then the filter, would work properly. And the real challenge is for the actual implementations, how do you actually characterize it and make sure that you telling the filter is actually what happens in reality. So that's challenging. I don't have a very good answer to it. It's sometimes trial and error. Sometimes you really need to work with specific sensors and figure out what their parameters are and go from there.
Okay, great. Thanks a lot, Andre. I think that's a good time to stop the first Q&A, but do continue to type in your questions. We do have another Q&A session towards the end. Before we hear from Sandy, I'll turn it back over to Lori for our second poll question. Lori.
All right, thank you. And coming up on your screen is that second question. We'd like to hear from you. What other sensors are you most interested in other than using GNSS plus inertial? And again, in this case, go ahead and select your top two. Is it odometer, vision, lasers or radar, maps, magnetometer, and pressure sensor? And showing 16% odometer, 47% vision, 65% lasers or radar, 32% maps, and 29% magnetometer and pressure sensor. So any thoughts on these results, Mark?
Again, I think this really speaks to the wide variety of applications and sensors that are available. The vision and lasers and radar are certainly very compelling, very, very flexible, and they can kind of do multi-purpose, not just for navigation, but also for many of the applications that were mentioned by Martin in particular earlier. I think we're ready to carry on. So our final panelist, who you've heard from but haven't been formally introduced to, is Sandy Kennedy, who is a graduate from the University of Calgary in 2002 with a master's degree and is currently the director and chief engineer of core cards at Novotel since last year, where she oversees the transformation of new and enhanced GNSS technologies into robust products for commercial and military customers. She has previously helped launch the Synchronized Position Attitude Navigation SPAN product line at Novotel, and her primary motivation in her career is to bring new positioning navigation capabilities to the marketplace to put to use in real-world applications. And Sandy's going to give us a nice talk about how you actually go together a practical system. Sandy, I'll turn it over to you.
Great. Thanks, Mark. So GNSS INS systems plus some other sensors as well, they're a great idea. Now we got to go build it. So the benefits are clear, but we really need to make sure we build a system that's useful and effective. So people will be relying on this information, or possibly machines will be relying on this information for unmanned systems, and your system needs to work within specification pretty much every time it's turned on and without onerous setup requirements. And the thing that really happens about, building a practical system that's being used by many different users is you are not assured of ideal operating conditions. So you really need to think of all the different ways that data could come in corrupted or not as expected, and know that the sequence of events that you follow in your testing may not be the sequence of events that your general user is going to do. The system also needs to be manufacturable and testable. Again, that working within specification and starting up every time with the same type of performance relies on low unit-to-unit variability, which has both a hardware component into it as to what sensors you selected to use in your system, as well as a software component in it. What kind of algorithms are you using, and are they reliable as well? And you need a repeatable build process. You've got to be able to make the same thing over and over again, because hopefully you have customers that want tens or hundreds of the same system, and they want to be able to have the same thing, and it's not being unit specific anymore. So a good starting place to think about the design, and I've laid this out as a little bit of a circular process rather than a defined progression. is all the things that you need to consider when you're making choices about what system you build. So the first one is defining your system requirements. And that is, is the system primarily being used to provide an attitude solution? Is that a really key parameter that's needed? Or is the system really relying on a position solution and bridging GNSS outages with a position is the most important part of your system? That can really have some big impacts on what you choose for your sensors. So then again, the next thing to consider is, okay, I know what I need to provide to my users. What is the operating condition that I have to provide this under? What I select for a sensor set, if I'm in an open sky condition with some nice dynamics in terms of fairly frequent turns, will be very different than what I'll need if I'm someplace with restricted view of the sky and possibly very long stationary periods and dwell times. The parameters really change for what you need for your inertial sensor in that case, for example. So definitely choosing your algorithmic approach comes next, and that appropriate sensor set. So the operating conditions, the algorithmic approach, and that appropriate sensor set is kind of these sort of could just be a little loop on their own here as you determine what it is you've got and what it is that you can do with it. And then the one part that is often really overlooked is once you've decided on that sensor set and what the requirements of your algorithms are and your user, you need to design a data acquisition subsystem to be able to bring all that data in for combination in some sort of fusion algorithm. So data acquisition details are often glossed over when discussing algorithmic approaches, but reliable system operation really hinges on this. You must have data that is got a correct time of validity on it. We look at, a block diagram like this, and the output of it is solution at time tk. So we are computing a solution valid at time tk, and we'll be collecting data off of all these sensors, possibly doing some more pre-processing on it. So we need to know how we're interfacing to each sensor, how we're providing the time out to it, or time stamping the data coming in, what are the associated latencies with it, so we can get down to what we need as input to that data fusion algorithm, which is data all valid at the same time. Or if it's not, we need to know how much different the time of validities can be in the given system, how much, say, a motion has occurred in that time that we're now going to neglect and lump into an error term somewhere. So really, we've got two types of data to deal with in terms of time synchronization. Synchronous data, and when I say synchronous, I mean synchronous to GPS time, because typically GPS time is your sort of master reference clock for your system. And these ticks here, we'll call them the even GPS time intervals, so not 2, 4, 6, 8, but like a 0.00 type of epoch. So you've had to disseminate your time out to other sensors somehow, and you're going to have data that comes in possibly asynchronous to that. So asynchronous is often when you can't control that other sensor. Things are just going to happen when they need to happen. Or asynchronous can be just a constant offset here, where you've got some latency between the time you gave something a trigger and the time it was able to respond and give it back to you. So in this case, this sort of offset here between GPS time and there is something that possibly you could calibrate, or possibly you think you can estimate it in your system, model it somehow. But always remember, if you're choosing to estimate or model it in real time, you've now have to make sure that you have the right observability conditions and sufficient convergence time for you to get a good estimate out of that. And you may end up with data that kind of comes in whenever, like possibly a camera exposure. You may trigger your camera on a given interval that's, determined by your system, or the camera may be triggering sort of opportunistically based on what it's seeing and how that processing is being done. But the really key thing here is that as long as you know all of the times, you can choose the right way to deal with this in your data fusion algorithm. But having that reliable time stamping as well as reliable data that doesn't have gaps or missing epochs in it makes your life a lot more simple in the long run. Sorry, I've got a bit of a delay on my keyboard from when I page down to when it happens. So here's an example with IMU data, because inertial sensors are pretty commonly used. And these are sort of three different ways that the IMU data gets synced to GPS time. I've got the input of the IMU data into a GNSS receiver because that's what I'm used to doing, so that's what I'm using in this example. So in the top example there, we're providing 1 pulse per second into the IMU, and the IMU clock will interpolate between those 1 PPS frame boundaries, has some smarts on board to apply a timestamp to the IMU data, provides that into the GNSS receiver already packaged up with the time of validity, which is great. The IMU clock there interpolating between those boundaries means that you may have a short or long epoch on right before the PPS frame. The other way that you can do it is you provide a high-frequency reference into the IMU, and the IMU will sync itself to that frequency. So now you get high-rate synchronous IMU data coming in. So you could know that offset from the synchronous trigger to data ready through calibration, or you could try solving for it with a timestamp when this data comes into the GNSS receiver. And then the last approach is your IMU could be completely free running. It's running on its own clock. It's just doing what it's doing, and it is hopefully providing you an input pulse leading the data message coming in. So that input pulse says, this is the time of validity for my data. Please precisely timestamp me, GNSS receiver, when I come in your front door, and then data will follow in afterwards. You've got some other ways that you could do it with slightly less precision without a precise mark input. These are kind of the three different ways. So for basic inertial sensor, you can already see there's quite a bit of variation on how it could interface with the rest of your system. So data acquisition is kind of common to all the sensors that we are looking at here. So now when we get down to choosing our sensor set. So yes, we've decided we want an IMU because we know that our GNSS receiver is not capable of providing us the solution all the time that we need for our system. So yeah, an IMU and a GNSS receiver, and then our other sensors as well. And then to kind of, tying back into what Andre was talking about, perhaps it's better to think of what input measurements are useful and just think of it as a general sort of external position, external attitude, or position displacement measurement coming in. So starting with our inertial sensor selection, what is the right IMU for your application really depends on what your application is. So bias stability, especially around the gyros, is something that can really affect what you're going to rely upon for your alignment method, as well as your convergence time. So overall biases are generally pretty high, meaning that we can't do, generally pretty high on a low-cost sensor, meaning that it's not able to do north-finding alignment on your own. And you need to be able to transfer in an alignment from another source. Maybe it's a GPS course over ground measurement, which would work great if you were in a land vehicle, like a tracked land vehicle. But if you're in a helicopter or a boat, that's probably not a valid assumption that your course over ground is going to match with the forward direction of your IMU axis. So then you have to look at what you're going to use for aiding sensors. So the dual antenna GPS system is what you need to be able to transfer in that alignment. Some other kind of more subtle errors that people don't always think of right up front is non-orthogonalities and misalignments in both the gyro and accel triads themselves, and then the gyros and the accel triads with respect to each other. Our math all assumes perfect right angles, and the gyros and accels being kind of coincident. If it's not, it has to be handled, as well as being perfectly orthogonal. Again, you could try to model that in real time, but that's going to put a requirement for observability of those errors, which may force you into some dynamics or conditions that you don't have access to in your application. Same thing with scale factor errors. It's something that may not show up for you unless you're under a highly dynamic application, but when you are, you may notice that effect. The noise level, for sure, what's the rate of output that you're thinking of getting this solution at? What's the smoothness requirement for it? How quickly does that noise integrate up into a drift for you? So all of this is kind of one big, kind of flows together. What do you have at your disposal for alignment methods? Are you able to tell your system all the configuration parameters it needs to be able to transfer an alignment? What kind of convergence time is required for a system? And what do you think you're going to have for GPS coverage? Just really considering the whole package. And then the unfortunate details of size and cost. What can I actually fit on my system? What can I afford to put on there? And export classification. The heritage of inertial systems is very much a military technology, so there are export controls around inertial sensors still. And then the mean time between failure. What's the lifetime of this product for me? How long can I expect it to run before it's going to break or I need repair? So moving on to our additional sensor selection, that second antenna and receiver to go with it. This is very useful for alignment. You must be able to measure or estimate the angular offset between your GNSS baseline and your IMU axis. So here, we're assuming in this diagram that the forward axis of the IMU is parallel, at least, to the line between the two GPS receivers. And then if you've got this system there for alignment, you probably want to use it for attitude updates as well, especially if you expect to be stationary or have constant velocity for long periods. When I say long periods, I mean, let's say more than 5 or even 10 minutes of same speed, same heading. But then you might run into the physical reality of your application, which is, can you actually bear the size of 2 antennas with sufficient separation on them? You typically want to have at least 1 meter separation to be able to get an attitude measure that's of sufficient quality to aid an inertial system for you. So from the polling question, I see that odometers were not of great interest to everybody, so I'll kind of go over this quickly. A lot of people think, I'll add an odometer to my system, perfect. Well, first of all, you need to have some wheels. You need to be able to mount something on the outside of your wheel as well, or you need to be able to rely on a sensor that's an odometer sensor that's already within your system, something like coming out of the CAN bus of your vehicle or something like that. And really the big question on a wheel sensor is, do you expect to have extended total GNSS outages? So total GNSS outages for more than, say, a minute. Because if you're going to be in partial GNSS conditions, being able to do a displacement measurement from your carrier phases over time is actually a much more powerful update than the odometer. People refer to it sometimes as satellite odometry in the literature. And then moving on to magnetometers. So magnetometers, again, they can give you a good indication of your attitude, but one thing you really need to be careful with is the quality control of the data. Magnetometers are affected by electricity and metal. We are usually in an urban environment. We're around a lot of other electrical sources as well as other vehicles, and we're often not in control of the environment around us, so it can be changing quite a bit. And then when you want to transfer that, say, azimuth measurement from your magnetometer into your INS, you need to know what the offset is between the two of them, as well as what your magnetic declination is, and any associated error with those. So what you get for the final sort of accuracy and standard deviation of your magnetometer measurement going into your inertial sensor fusion really determines how useful that magnetometer will be for you. And then the altimeter or barometer, this comes down to how can you package this for your customer. Often your nav system needs to be in an environmentally sealed enclosure. So then where do you expose that sensor to the ambient air? If your barometer sensor is inside your enclosure, you have basically a time lag between a height change and the pressure change inside that enclosure. So again, depending on your application, that might be all right, but if you have a very dynamic in the vertical sense application and you aren't able to expose that sensor out to the ambient air, it might not be as much value to you as another application. So if we think about this in more of a generic sense, so you could design your system to just accept the generic input that the overall total system user has derived. So the external position of the IMU, or some known point that you know the relationship to from the IMU, or an external attitude measure, same thing. Provided that this external input data can be timestamped correctly and provided to the GNSS INS system fast enough, they're very useful updates. Again, referring back to what Andre was mentioning, this external input data needs to have a correct quality indicator with it. That should be a standard deviation that truly reflects the error, and that it doesn't add any more unknowns to be modeled into your system. So ideally, if all your input data that you were providing to your system was beautiful Gaussian white noise, this would be a great approach, but you need to understand both the characteristics of the data that you're putting into the system as well as the latency associated with it. So I always refer this as the "you bought it, you can break it" model of a system, which is if these criteria are not met in the external updates that you're providing into the system, you can get suboptimal performance. And suboptimal performance typically means a lot of customer support calls, which is sometimes interesting, but not a lot of fun for anybody involved in the long run. So takeaways from my presentation here, which is select the appropriate sensor sets for your application. Know the requirements of the target application that you're intending the system to be used in, and understand how your individual sensor errors impact your overall system error budget. The same level of error in a low dynamic application won't have the same impact on a high dynamic application, and vice versa. Start with a really reliable data acquisition subsystem in both hardware and firmware. This is the foundation. It's the unsung workhorse that's underneath all of the flashy algorithms you layer on top. And those flashy algorithms that you layer on top, make sure that they're reliable and robust data processing, something that's going to work in non-ideal conditions, something that isn't very, very sensitive to what, say, your initialization looks like, or sort of a set of events that the system encounters. And sort of to confirm all of these aspects is test, test, test. There is no substitution for real-world data. Simulation is a great starting point, but real-world data is what will let you know you've designed the system as you needed to. And that is the end of my slides. So back to you, Mark.
Great, thanks a lot, Sandy. I think you've done a really good job highlighting how multifaceted these types of systems are, and there is no real one-size-fits-all solution, even if that might ultimately be what you're trying to accomplish. You really need to consider a lot of different aspects. So before we get to our Q&A, and again, I encourage you to enter some more questions if you have any of our experts. We'll get to those in a second, but we'll start off with just a little bit more information about these webinars. This webinar presentation, as well as the ones from Monday and the one that will come on Friday, will all be available in PDF format on the Inside GNSS website. You can see the link at the top there. Also, don't forget that you will also be able to download the actual, view the actual presentations themselves. This is also a friendly reminder that there is a third installment of this series on Friday, and again, you can go ahead and head to the website from Inside GNSS to register for that one. It's going to focus a bit more on the applications that are involved with unmanned systems. And then there's some basic contact information from our sponsor as well as our three panelists. So before we get to our Q&A, we have one last poll question, and Lori, I'll turn it back to you to take care of that, please.
Okay, thank you, Mark. And again, on your screen is that third poll question, and we'd like to hear from you. Which best describes your GNSS Plus inertial application? And in this case, we're going to ask you to select just one: low dynamic and high accuracy, low dynamic and low accuracy, highly dynamic and high accuracy, and high dynamic and low accuracy. Okay, so 32% saying low dynamic, high accuracy, 4% low dynamic and low accuracy, 52% high dynamic and high accuracy, and 13% high dynamic and low accuracy. So any comments on those results, Mark?
I can't say I'm overly surprised with this. Accuracy, of course, is the ultimate goal of pretty much any navigation system, and regardless of the dynamics, that appears to be what most people also think as well. So hopefully you've gained some insight from this presentation that will help you in attaining the accuracies that you need for your particular application. So having said that, we'll start the Q&A session. I'll turn this one over, first of all, to Andre, but then I'll open it up to everybody else. This is a question from Bryant, and he asked, regarding deep integration of GNSS with other sensors, such as inertial, can you comment on the merits of vector-based versus scalar-based processing approaches within the receiver?
Sure, and I'll try to give a relatively short answer because you can write a dissertation on this topic. You know, like I'm personally prefer the scalar-based approach when you integrate with inertial. Vector tracking, in my opinion, is very useful when you don't have inertial. Then you can have, so to speak, strong satellites helping you weak satellites. But when you do have an inertial, my preference would be to actually have separate tracking channels for different satellites and aid those tracking channels with the inertial. For example, the best thing probably you can do is to increase your signal accumulation time, do coherent and non-coherent integration approaches, and integrate the signals for as long as you can, and then estimate signal parameters based on the integration results. You can do the vector tracking as well. I think in this case, just the signal accumulation process in the AIDEN part becomes a little bit easier and less demanding as compared to when you do it based on the inertial. But you know, the problem there could be in terms of the reliability and robustness of the solution. For example, if it happens that you're in an urban environment and you're tracking a non-line of sight multipath for one signal, and then you mixing everything into one common filter, and then that common filter aids your signal integration process for all other channels, it becomes really difficult to identify this corrupted measurement channel, and as a result, it will influence all the other channels pretty quickly, and you know, can basically pull your solution completely offline direction relatively quickly. When you're doing the separate channels, then the integrity monitoring or measurement quality is much more straightforward as compared to vector tracking. So again, that's my personal opinion. I may be a little bit biased towards the scalar-based approaches because that's what I've been mostly developing and believe in, but nevertheless, that's what I think.
Great. Martin, Sandy, anything to add to that?
No.
I would just second what Andre is saying there. The vector-based, deep integration approach is great as long as everything is working out well for you. But when you get into difficult conditions, you can put yourself in a place where you've somewhat ruined your GNSS sensor and you're no longer getting valid information off of it. So if you'd let things run a little bit more independently and been able to do more of the integrity monitoring, you have a more safe system overall.
Okay, interesting. And Martin, did I hear you say you had nothing else to add?
No, I think Andre and Sandy captured it very well.
Okay, wonderful. In that case, I have a question for you. This is from Ray, who asks, how will lasers/camera sensors determine if a referenced object is moving or not?
It's a very good question, and it's also it kind of points at a very important set of functions you need to include if you use these laser and camera sensors to your solution. In a sense, if you do a feature-based approach that Andre was alluding to, it is very important in when you extract these features to include an integrity monitor that actually checks out if these features are moving. So in other words, if I would observe a variety of planar surfaces, and one of these planar surfaces would be associated with, for example, a vehicle that moves, you need to actually be able to detect slow motions of that particular feature as well by, for example, residual checks or methods that are similar to RAIM, for example, Receiver Autonomous Integrity Monitor, that you would typically do in GNSS. Of course, if you do this with feature-based methods in cameras, now you need to establish that, okay, what does this mean for a feature in 3D space? What the motion of that feature mean for the pixel motion that you would observe in your cameras? So what we have seen in the past, some work that Andre and I did together actually, is that if you're able to detect these things very good, but you need to include it, because if you're not including any integrity monitors for these moving features, you will actually have a navigation solution that will diverge, or it will just be drift away as well.
Okay, great. Thanks a lot, Martin. Andre, since you've obviously worked on this as well, any comments to add?
Well, I just want to say that, as Martin was saying, you can obviously use RAIM and adopt it from the area of GNSS, but the word of caution there, obviously, the RAIM and GNSS generally assumes a single failure case. When we talk about the vision-aided or image-aided navigation in general, you can't quite assume that because you may have multiple moving features in your field of view. So you really have to be careful. Again, I think having the inertial as a sort of a benchmark to check against, I think is very useful when you're doing the GNSS plus inertial integration. And that's a great tool to determine bad measurements, quote unquote.
Yeah, I agree. I think the challenge, of course, is ensuring that your inertial solution is also good, because they're not impervious to errors as well. Sandy, the next question is coming to you. This is regarding the oscillator quality, and many people might be aware that it's it's very important for tracking within a receiver to have a good oscillator. But what impact does it have in terms of the performance of an integrated nav system?
Right. So as I mentioned, your GPS time is typically used as your master clock for everything else in the system. So that means that if you have lost tracking for some reason, you've gone indoors or something like that, you're now relying on just the native capabilities of your oscillator, because you're no longer able to steer it or model how it's different from the true GPS timescale without your measurements. So that's something that you need to consider. If everything's synced together, everything will drift together, which is probably okay. At very, very high-end accuracy systems, you may end up with a problem in terms of if you, for example, are taking an IMU measurement and you think you have a 1 millisecond interval, but you actually have a 1.1 millisecond interval. If you had significant motion in that extra 0.1 of a millisecond, it will start to degrade the performance of your system as well.
Great, thanks, Sandy. Anybody else want to add anything to that? I will take silence as a no. In that case, Andre, the next question is to you, and Martin, you're welcome to add to this as well. The question is from Simone, and it asks, can image-aided navigation systems be used for integrity purposes in civilian aviation, or is it too demanding from a computational point of view?
I think from the computational point of view, you're probably going to be okay. I mean, if you're not really limited in terms of the processing power, it's probably going to be okay. The challenge is to really make sure that your image-based navigation is good. And we just talked about the problem of image-based navigation and the ability to detect bad measurements for image-based navigation as well. And just for image-based navigation, when you're doing it based on the LiDAR, it's actually a little bit easier because you measure the range to the objects directly. When you're doing it based on the vision of video cameras, you don't measure the range to the objects, and you either have to use the displacement for synthetic stereo, or you have to use stereo cameras, and it just becomes more difficult. How do you control the measurement quality on the image-based part? So if you nail down the image-based navigation approach completely, which is not, in my knowledge, is completely done yet, even from the research perspective, then sure, I think from the computational point of view, you should be fine.
Wonderful. Martin, anything to add to that? Perhaps from the integrity side, can it actually meet those requirements?
Yeah, actually, I was just going to say that. I think there is, if you look at laser-based navigation, I think in terms of the integrity point of view, I think there has already been done some research in looking at these aspects. Of course, a laser-based system on board of an aircraft, is a significant investment, as well as certification issues are a big issue. If you go to the camera, it becomes a little bit harder to quantify, and I think there's a lot of questions to be answered to say, okay, what kind of failure modes do exist in these cameras, and what are the failure models look like just for nominal performance versus off-nominal performance. For integrity purposes, if you want to really do a good integrity analysis that you would typically have to do for an aviation application, I think there is still not sufficient information out there right now to be able to meet these integrity goals that we have set for the aviation community.
Great, thanks a lot. Sandy, do you have anything to add to that?
No, I don't think so. I think Martin and Andre covered that quite well.
Okay, sounds good. We had a question. Let me just find it on my screen here. This is a question from Mushtaq. I apologize if I'm pronouncing that incorrectly. The question is, how is the performance of your system affected by the data rate for GNSS and inertial sensor? And I will expand that to include any other sensor you may have available.
Okay, I'll start with the inertial sensor. The data rate on your inertial sensor, how important that is depends on what type of data you're getting off that inertial sensor. So if you're getting a straight acceleration or an angular velocity measurement, angular rotations off of that sensor, that's sort of an instantaneous snapshot in time if it's just a single measurement. And if that's the case, then you would need to have quite high rate data coming off of it to be able to capture all the motion. Typically, for most better sensors, they're going to give you a delta theta, delta velocity off of there. So that's already going to be accumulated for you. So that means if you take data at 100 hertz, you aren't missing any of the data that occurred in that 1 millisecond period, 10 millisecond period. You are getting all of the motion that occurred, but you're assuming that it happened linearly across that interval. For most applications, that's a completely fine assumption to make. Moving on to your aiding sensors, the data rate for your what you want to do for an aid into your mechanized INS solution, you need to have it coming in at a rate that has allowed the inertial error to grow enough that you can observe it in that update. And also that the aiding source that's being used at whatever rate it's being used isn't too highly correlated. So an example of that is, say you think, oh, great, my GPS receiver is capable of 20 hertz measurement, so I want to use 20 hertz positions to update my INS. Well, in 120 hertz interval, your INS error may not have grown significantly for you to actually observe it in your update measurement. And at 20 hertz, your GPS positions from epoch to epoch will be quite correlated because of both geometry and multipath being correlated over that period as well. So in that case, you would get probably actually a better accuracy solution with more correct statistics coming out of your filter if you had stuck to a 1 hertz update rate, or possibly even lower than that, maybe once every 5 seconds.
Wonderful. Thank you. Anybody else have something to add to that?
I think that was covered fairly well and very thorough, so I don't have anything to add.
Okay. In that case, we'll move on to our next question. Martin, this one's for you, but again, people are welcome to contribute afterwards. Obviously, there's a lot of research being done in terms of combining very specific sets of sensors that work in very specific environments. And the question is how important is context awareness within the field of unmanned systems or system integration?
I think it's very important, especially when you start operating in these challenging environments where you see a lot of environmental changes go on. So the context that you can derive from observing the environment also drives maybe the performance of your sensors within that environment, and as a result also maybe the way you want to reconfigure your filter to get the most optimal solution. So rather than using looking at the output of your integrated solution, you may also already want to look at the sensors beforehand and make an inference from the sensors about the context in which you're operating. Besides that, what you find out is if you have an intended function, you may go to different phases of operation, and to make these mode switches, the context in which you're operating now needs to be performed by an automated function rather than by a human operator, or pre-processed by an automated function and then given to a remote operator. So I think context is essential, especially when you're, for example, do these applications where you move and do law enforcement or search and rescue or mapping in urban environments where you really have to have multiple phases in your operational scenario. That's it. You still there?
I can still hear you, Martin.
Sorry, my mistake. Andre, anything to add to that, or Sandy?
No, I'm good.
Okay. In that case, we'll ask one last question, and this question has kind of come in different forms, so I'm paraphrasing several people here. The discussion has been around time synchronization of data, how important is it, and all these things. I think, Sandy, you addressed that fairly well. Perhaps, do you have any words of wisdom or perhaps words of caution for how not to underestimate this task as you go about developing your systems? And maybe, Sandy, I'll start with you on that one.
As in, what's the biggest mistakes for you to avoid, you mean?
Well, that or I know from my own experience, people tend to underestimate the effort involved here.
Oh, yeah, for sure. I mean, a lot of people underestimate the precision that they need. So for even a low-cost system, I'd say that a 1 millisecond time accuracy is the maximum that you want to put up with in your system. Because depending on, just think of what can happen or what can change over the course of 1 millisecond. The other thing that can happen is if people are relying on just a fully software method of timestamping data. So say data is coming in the front door of your processing system, wherever it is, and you figure, oh yeah, I'll just grab system time as I'm processing those bytes in my receive task or something like that. Well, that can be a very variable number for your latency, depending on how heavily loaded your system is doing other things. So it's one of those things where an unmodeled timing error can masquerade as a lot of other errors in your system, and you can spend a lot of time trying to optimize on the wrong thing. An example I dealt with was my timestamping was actually broken on a very good quality navigation grade IMU. And I was looking at this, and my errors were getting worse over time. So the longer my system operated, the worse error I was getting. When I was forcing outages at different times, and I was chasing the idea that maybe it was something temperature-related going on because the system had been running longer and heating up. And I probably wasted about 2 or 3 weeks on that before I realized my timestamping wasn't working properly, and what I was seeing was the drift of the inertial clock with respect to GPS time. So it can be a lot of wasted time, and in that case, it was a very high-quality navigation-grade IMU, so it was in some ways easier to spot.
Right. I think you really hit the nail on the head there, and I've been getting the cue that we're to wrap up, but I know, Martin, you had mentioned before you spend a lot of time doing that in some of your work, so I guess the end message is, really take it seriously and really pay attention to it, because it can cause a lot of challenges and a lot of problems. So having said all that, that's about all the time we have for today. I'm going to turn it back over to Lori for the wrap-up. Lori.
All right, and thank you. And folks, before we do sign off, I'd like to take a moment to thank all of you for joining us and trust that you found today to be of value. Very special thanks to our moderator for today, Mark Petavello, and our speakers, Martin Uttehag, Andrei Soloviev, and Sandy Kennedy. And, of course, our sponsor and co-host, Sensinor and Inside GNSS. Also would like to thank our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support. And most importantly, thanks to each of you for joining us. This is Lori Dearman saying, hope we see you on the next one on Friday, and have a great week. Bye for now.